As you get older, well, as I get older anyway, I notice more and more that there seem to be a lot of things in software engineering and programming languages and how we write software that we knew in the 80s and that we somehow forgot and are now rediscovering. And Concurrent ML is one of those things that we should be rediscovering anyway. So, well, obligatory slide about what I do is I'm CEO of a company, of a software company in Germany called Active Group. We do software and things from social pedagogy to semiconductor fabrication, but we do it all using functional programming. And well, we also run a German language blog on functional programming. We also run a conference that is sort of a little bit like this one, and it's almost even better than this one, but it's in Berlin, Germany. So if you're interested, it's February, so that promises to be pretty good. Anyway, so a long time ago in a former life, I was a lecturer and researcher at the University of Tübingen, and I taught a course on concurrent programming, and I really designed that course from scratch, and I was looking for good textbooks, and I came across this thing called Concurrent ML, which seemed to me really the paradigm that was best suited for writing concurrent applications, and I ended up then implementing Concurrent ML for a scheme implementation called Scheme 48. I later designed a Concurrent ML implementation for an obscure language called Star that you can still find if you look for it. And some people might know that I wrote the 6th edition of the Scheme standard. So even though this talk is called Concurrent ML, most of the talk today is going to be in Scheme. And I just got praised earlier this week for doing a talk that caused the audience to do mental gymnastics. So that might be one of those talks too. Anyway, but really, so this is the best book on concurrent programming. And John Reppy keeps promising me that there'll be a new edition any day soon. But even if there isn't, it still is the best, and you should totally get that. And I do not have a single example that's better than the ones in this book. So that's what I'll run with today, and I'll say a few other things. So fast forward, though. So I taught this course in 2002, and I was doing a tutorial at the workshop for commercial users of functional programming in 2011. And I kind of remembered that, and I remembered Concurrent ML was all about message-based concurrency. And you might work today in an environment that gives you message-based concurrency, such as Akka or Erlang or something like that. But I was doing an F# tutorial, and I discovered that it actually has a little framework for doing message-based concurrency called, oddly enough, mailbox processors anyway. So I figured I would just go and do a little example, one of the examples from this great book that I remember from the Concurrent ML book, and just rewrite it in F# to show people how things are done in F#. And you can see here's a little network. Well, it's kind of an academic example, but you express the Fibonacci numbers as a network of concurrent streams. And so you have data flow going around, and I think you recognize it. So you kind of, so you always add sort of the previous two numbers. And so you always sort of have one number going in there, and you need to delay one by one, add them, and then things goes around and around in this network, right? And so I thought, well, it's just going to take me like a half hour to do it in F#, and I couldn't do it. I ended up doing a different example, but the reason was that really the F# mailbox processor is something that, even though it's based on message-based concurrency, it really implements something that we know as the actor model. And the actor model, here's a picture of the actor model. That's it, right? You have things and you send messages to processes or to actors, right? And so if you're into functional programming, you always want to do things that compose. And sort of looking at that picture, you realize this does not compose, right? Specifically, does not compose in the way that this requires composition, right? And so I ended up trying really hard, so never mind that code. So trying really hard to implement another example, a merge sort, but I really ran against that fundamental restriction, and it just turned messy and unsatisfying. So abstractions really matter, abstractions that you use for whatever it is, in this case, functional concurrent programming, and I would argue that composition matters as well. So I'm going to tell you a little bit today about the facilities that exist in Concurrent ML that enable abstraction and composition, and that have since mostly, not completely, been forgotten. So not completely, I mean Concurrent ML, even though, so was originally developed for something also long forgotten called Standard ML of New Jersey, a Standard ML implementation. Well, see some people here who might remember that. Yeah, but pretty dead these days. Anyway, but it still exists with a couple of other almost equally obscure programming language implementations, a couple of ML implementations, but the majority of these are sort of descendants of Scheme, like Scheme 48 and Racket and Guile. Guile has a pretty new and shiny implementation of Concurrent ML. And Star, and there's also a Haskell library that implements Concurrent ML, but that seems to be pretty dead as well. All the other ones are, well, maybe the environments that they exist in are kind of dead, but within those they're well maintained. So I'll show you a little bit why a couple of things are not Concurrent ML, and I can't even remember why I had forgotten that in 2011. So Erlang and Go and closure core async and Akka streams and whatever, or Akka generally are not Concurrent ML. So here is, so I hope we can make out all the letters. So here is again the picture of that Fibonacci network. If you sort of look at the original figure again, you can see that the edges have been labeled as are these boxes in the middle. And here is a Concurrent ML solution written in Scheme. So I don't know how many of you people have done Scheme. Doesn't really matter. Scheme is a very simple language. So we're defining just a function that creates a Fibonacci network. We're saying we're creating, so these edges here, we're implementing them with a Concurrent ML mechanism called a channel that connects two things or that connects various things in this network. And so we're creating channels for each of the edges here, and they have the same name. So here's the out channel. Here's C1, C2, C3, C4, C5, and we just create channels. And then we hook up the components to those channels. So for example, here's the delay component, which sits between C4 and C5. Here's the copy component, which sits between C2, C3, and C4. Here's the add component, and you can hopefully see that the program corresponds directly to this picture. Is that clear? Okay, good. And so then what remains is to actually implement the abstractions that occur in that program. For example, here's the add thing. So add is this component. It has two input channels and it has one output channel. So it has parameters in channel 1, in channel 2, and one output channel. And really, well, you need to focus for a moment here on this part. It just says, well, to the output channel, we're going to send the sum of things that we receive from input channel 1 and input channel 2. So that seems pretty intuitive. We'll later see that there's something wrong here, but we'll get to that. And you just need to keep doing that, right? As numbers come in, you need to spit them out at the other end, which is why it says forever here. So this forever thing, here's the engine that keeps all of these components going. It's a function called forever. It takes two arguments. One is called init, which is the initial value that you feed around this carousel, and this function f. And what you always do in Concurrent ML is you spawn a thread. That's what that spawn thing does, and you feed it a thunk. And here there's just a loop that just says, well, we're going to go round and round and round, and each time we're going to apply that function f, right? And in this particular case, you might have seen it says forever false, which is because we're not interested in the value here. We're just interested in the effects, but we'll later see an example where we're actually interested in the value. So there's the forever thing. So here's the delay. Here we're actually interested in the value. Delay is sitting here. So we need an initial value that we can use for this loop that's going on, and we have one input channel and one output channel, and so we alternate sort of between receiving something and sending something out, right? And this value will either be false when we're sending something out, or it will be the value that we received, which is something that we'll be sending out on the next round, okay? So you can see here's this if, and it alternates between sending something to the out channel or receiving something from the in channel, right? And the return value of this becomes the next v, and then gets sent out here, okay? So we start with init, and you might remember that there was this one number that we fed in. Here's the copy. Here's the copy function. It has, well, you need to read it from the right. So it has one input channel, two output channels, ouch1 and ouch2. Again, it goes on forever. and it receives something from the input channel, and it just sends it on to the output channel 1 and the output channel 2. So as with at, there's something wrong here, but we'll get to that later. This program is actually going to work, but you might notice that there's something oddly disturbing about this, right? I should note, yeah, so what we've used here are two functions called send and receive, and for you ML and Haskell and Miranda programmers, I've put in type signatures. So you have a channel of type that carries values of type A, so these percent things are type variables, and sending something is just going to not return anything. You feed it a channel and a value to put on that channel, and receive, you just give it that channel, and it will give you the value that somebody else put in there. And these are synchronous operations. So a send and a receive have to meet for both of them to succeed. Okay, that's important if you're used to a framework where these things are asynchronous. In Concurrent ML, they're synchronous. They have to actually meet simultaneously. So here's what might worry you about that copy function, is in that we receive a value, and there's an ordering here. It first sends something to out channel 1, and then it sends something to out channel 2, right? And if you have this kind of ordering in concurrent programs, well, you might remember there might be deadlock issues. There aren't in this particular case, but they might occur in this case. So what you really want to do is you would like to not say which of these has to happen first, right? One of them will have to happen first, but which one is right might be determined by the other side of those channels, and you can't see that on this side, right? So what we need is something that's called selective communication, if you will, where you say, well, you know, here's a number of things that might happen, and I'm going to wait for any of those to happen, and then, well, I'll do something based on that. And so a big question in the design of concurrent programming frameworks is, what are the things that you can do selective communication on, right? So, for example, so now we're going to jump to a few other languages. So for example, Clojure, right? Clojure comes with a message-based programming framework called core async. And you can write a copy function here. I'm going to gloss some of the thorny details to get back to them later. And this thing here is like this bang thing is receive, and this other bang thing is send, right? And as you can see here, we get a value, we receive a value here from the in channel, and then we do selection between those two out channels, right? So this alt thing says alternate or something like that. It says one of those two things might happen. And in this case, also the communication is synchronous. So we're going to see which one goes through first, either sending V on out channel 1 or on out channel 2. And then we're just going to send it, then depending on whether we actually succeed in out channel 1, then after that, we're going to do out channel 2 or vice versa, right? And this does not have an ordering issue anymore. So that's pretty neat. So Clojure, core asyncs comes pretty close, but we'll see, you know, pretty close is sometimes not enough. So anyway, so of course, Go is the go-to language these days for concurrent programming. You might have noticed this thing alt here is syntax, if you know Clojure. It's a piece, so it's implemented in a library, but it's still a piece of custom syntax. And in the case of Go, there's actually something called select. And it's not part of a library, it's baked into the language, right? But you can basically do the same thing. You can send V to out channel 1 or out channel 2, and you can see which one of those succeeds first, and then you just send it to the other one, respectively. But if you think about it, you already notice, well, how is this? You know, in this case, it's fixed, right? We have 1 and 2 always, right? But what if you have a list of those? How does that work out, right? So in Erlang, of course, and so Erlang is also based on message-based concurrency, but it has this actor model. So when you do this in Erlang, you realize that there aren't any channels. You don't send something to a channel, you send something to a specific process, right? Whereas to a channel, multiple processes might attach to a single channel. So this really is just sort of a translation in notation, but not really in spirit. Well, this copy function does copy 1 forever. It receives one value V, and then feeds that to output process 1 or output process 2. And, well, bang is often asynchronous, so there's maybe the ordering issue doesn't occur so much in practice. And there's subtle issues with this. So, but we can't even really talk about the issues that we talked about before, right? The selective communication is something that we can only do between receives in Erlang and a timeout, right? F#, same thing. Essentially, the communication between these mailbox processors, often that's shortened to agents, is always asynchronous, so there's no way to even talk about selective communication between different send operations that you have. Does that make sense? Okay. So anyway, so how does that work in concurrent ML? Well, in concurrent, so you certainly need a name for the things that you can do selective communication on. And if you look at the Concurrent ML book, it will call that an event. I find that a little bit ambiguous, but I kind of like the idea of a send and a receive meeting. So I like to call that a rendezvous. So that's what that RV thing is. It's two or some parties meet on something. So in this case, there's a select function. You feed it several rendezvous, and it will try to make one of them succeed, and will give you the payload value that comes from that. And then there's two versions of send and receive that don't just do it, that don't just perform the send or receive, but that instead give you the rendezvous that if you try to select on it, will perform the actual send or receive. Okay, so these are constructors for those rendezvous, and here's something that you can do with them. Does that make sense so far? So now you have these things, and you can immediately think about, well, if you're a functional programmer, you think about combinators for these, right? And the simplest combinator that you can imagine is that, well, if you have a rendezvous that produces an A, you might want to do something with the value that comes out. And so, well, you express that in the form of a function that accepts an A and maybe gives you back a B, and you can wrap those two things together and give you a rendezvous that produces a B, right? It's like map, essentially, but we often use that with an effect in that function. So, and you need this for this. So you can use this for a version of copy that uses select with concurrent ML. And here's how that works: is, well, you make rendezvous for sends on out channel 1 and out channel 2, right? And then you use wraps on each of those individually to then do the send on the other channel respectively, right? And then you do a select around that. That works. Okay, and again, this is the version that does the right thing. And you can do the same thing for add, and you can see the same pattern here is in that, well, for add you need two numbers, not just one as in the copy, so the code gets a little bit more complicated. But in this case, so you have a select on receive RV on inch 1, a wrap on receive RV on inch 2, and you wrap things around those where you see, well, here's the receive on the other one. Can you see that? Nod. Everybody nod. Okay, good, excellent. Doing well. And we cons those two values together, pass that out of the select, and then add them and put that on the output channel. Okay? So, and then things work out. So again, but select again is this thing. It goes from a bunch of rendezvous of A to A, right? It'd be nice if we could do that. So that's not what we usually try to do in functional programming when we're trying to do composition. We really want to stay within rendezvous. So there's a more primitive construct in concurrent ML, which takes a bunch of rendezvous called choose. And it doesn't just immediately give you back the A. It gives you back a rendezvous of A. And then you can combine that with other rendezvous and do something with that. And then later, when you really have built up your entire description of your rendezvous, then you can sync on it and select. If you look at the type signature, you can see that it's essentially just a composition of those two, right? You choose, you create a rendezvous that does selective communication, and then you sync on that. And so that's how that works. And so you already have a nice algebra here. And of course, so in your typical, modern concurrent language, usually your selective communication is going to be restricted to certain kinds of rendezvous. Usually it's like send on something, receive. Well, often it's just receive on something or a timeout. Sometimes it might be sends and receives. But there's, of course, all kinds of other rendezvous. There's timeouts. You might have different kinds of channels. We'll see one more kind later. you might have access to shared memory, I/O to sockets, I/O to files, and things like that. And of course, in your concurrent program, you would like to be able to combine all of those in selective communication. And it's always a bummer when you have to go to an API that only allows you to do some of them. I mean, if anybody has ever written like a runtime system for a programming language where you have to go to like Unix select, you know how frustrating that is, that it can only do file descriptors. Yeah, well, you know, right? You only do file descriptors and timeout, and you have to somehow get everything into that world, right? So this is much, much nicer. So not just that, you can build your own, right? So for example, something that you might sometimes want is swap channels, where you don't just send a value to somewhere else, but where you exchange as part of the rendezvous a value. And here's a R6 or as record definition, which just says, well, a swap is something that has a single field, which is a channel, and here the comment says what the channel carries. The channel carries a pair, so you swap things, it is a pair of the value that you're sending to the other side and a channel for the value in the other direction, right? So, and we just stick a new channel. Whenever we make one of those swap things, we always stick a fresh channel inside, and that works out just fine. But, so again, if you look sort of in the center here, you can see the same pattern again, is if you're swapping, you don't know, right, which one of the two parties to the swap is going to be able to execute first, right, the send or the receive. So you just do a selective communication on the receive and the send. And depending what that is, you either, so for example, if receive succeeds, you will get a pair out of the message that's coming in and the channel I can use for sending my message back to the other side, right? And then I send the message to the other side, and I produce the value that, that I got sent. And here's the other direction. If the send succeeds first, then, I send the channel on which I will receive the value from the other side to the other side, and the other side will then send something on that channel. And this way, things will just cross over. So that uses the choose combinator. There's another combinator up there which says guard, which is there to make sure that we always allocate. So guard just takes a thunk that produces a rendezvous and converts that into a rendezvous, because each time the rendezvous executes, if you will, you need to create a fresh channel up here. So each time it executes, that thunk gets run. So here's guard, takes a thunk, produces a rendezvous, and coerces that into a rendezvous. Okay. So there's also, if you read on Concurrent ML, I'm not going to fully expand on that, but there's also something very powerful called a negative acknowledgement. But it really goes to the power of the system. If you imagine writing a lock server, right, in this world, right, you want to acquire a lock. So if you want to acquire a lock, that means you need to send a message, you need to express your desire to acquire a lock to the lock server, and the lock server is going to look up, is that lock going to be available, and it's going to make that available to you. But by that time, you might have lost interest because acquiring that lock might be part of a selective communication, right? And so the lock server would like to know about this, that you've lost interest, right? One more reason why I like this word rendezvous, right? Because, well, I think it's a nice metaphor of what's going on. So I don't have a complete lock server, but the way it works is the client says, creates, so with NAC it's sort of like guard, but it creates this NAC rendezvous, which you're able to synchronize on if this party loses interest. And the pattern is always this: the client creates this NAC rendezvous here and sends it over to the other side. And the other side can then use that to determine that we've lost interest. Okay, so here's that pattern. So we have that NAC rendezvous. We create a reply channel that the lock server can send us an acknowledgement. We spawn a thread that will send our request to the lock server, and then we wait for the reply. And then the server, essentially, well, it receives a request. The request contains a reply channel and this NAC rendezvous, and it just selects between those two things, right? Either we're able to acknowledge, oh yeah, and again, a rendezvous is two parties getting together, right? So in this case, there really is agreement on not only did I give you the lock, but you also took it. And so here you can then commit to the lock having been acquired, or you have this NAC, in which case you can abort and give the lock to somebody else. So that's the most complicated bit. But your concurrent programming framework, try to do this nicely, right? You will find out that it's pretty difficult. So all this, I've getting ready for this talk and just thinking generally about concurrent programming, I've been trying to think about what it is that really is nice about concurrent ML. Erlang is nice in many ways, but it's not great on composition, right? And one of the reasons it's not great on composition is that the fundamental model that's built into the language is a couple of things that are put together, right? You have that process. A process has to run on this receive end construct that we've seen. A process is wedded at the hip with a queue of things that go into the process. And so it's several things, well, the closure people would say a couple of things complected together. And we know it's a very useful thing for building systems, but it's not the only thing that you could build to make your concurrent system run. And so channels sort of give you a nicer picture or a more primitive picture in that you have this channel here, and every process, and you can share that channel between different processes, and everybody can write and read, and that makes it much nicer to build composable frameworks. If you're a Clojure fan, you might have had high hopes for this new, well, it's not new anymore, but it just got out of alpha, I think, a couple months ago, something called Core Async, which gives you channel-based, message-based concurrency. So you might think this is going to give me, or I thought anyway, it was going to give me the power that I was used to from Concurrent ML, specifically because its core API does have combinators, right? So, well, so here's the official documentation for the merge combinator, and you can see, well, channels, it has channels that go in, and you kind of think, oh, that's kind of nice, but then you realize, well, it's a combinator on the read actions on those channels, and that's, those are the only things that you can combine this way, right? None of the other actions work that way. You can define, you can write your own combinators in Core Async, but the way that always works is that you need to have what's called a Go block. They thought they were doing themselves a favor by making it attractive to the Go people. And a Go block will then return a channel which will receive the return value of the code inside that Go block. So you can kind of go from channels or whatever it is to a Go block back to a channel, and you can use that for composition, but it doesn't work very well in practice. In particular, this sort of cycle here has like a 10x performance overhead. So that's how that works, right? Is you have a Go block, you have a bunch of channels going in, you write your combinator code imperatively, you go through the execution machinery of the Go block, and then you get a final channel for the result. And so it kind of looks like it might work, but in practice it doesn't really go there. And the reason for that is also that Core Async complects a couple of things, namely lightweight concurrency and message-based concurrency, right? And I think that's one of the things that we've forgotten from the 80s, is in the 80s we knew how to build programming language runtimes that had extremely cheap threads, right? Well, Erlang still knows that, right? But most everybody else seems to have forgotten, and so that created the need to somehow put lightweight concurrency on top of the heavyweight threads of the language runtime, right? And so in particular, if you're on the JVM, then the native threads on the JVM are pretty expensive. And that led people to believe, well, it's because they're threads, right? It's because they're threads and they're not actors, and actors are much cheaper, but of course it has nothing to do with any of those things. It just has to do with the fact that that the community at large knew about more efficient programming and implementation machinery. And so that's why Core Async, I know I'm rambling a little bit, but maybe it'll all gel and make sense in the end. Why Core Async has this Go construct, because it creates sort of a special execution machinery for the code that's in here. Code in here doesn't really matter, but what matters is the macro will compile that into what they call a state machine. And if you know C#, they also talk about a state machine that they're going to compile it into. But really what it's about, it compiles into a bunch of continuations that have a shared representation. And all that vocabulary has also been lost since the 80s. So there's that. So I'm trying to tell you where things have been conflated so that maybe in your mind, by the time that you go to sleep overnight, they will clear themselves up. if you talk to people who do like modern message-based concurrency frameworks, such as Akka, they're all obsessed about buffering and backpressure. Specifically, the core async people are obsessed about backpressure, right? And unfortunately, it's not that easy in that kind of framework because you have threads. And so does everybody know what backpressure, what that is about, right? Is essential. So what happens is that, well, you might have, specifically if you do asynchronous communication, you're going to have a queue somewhere, some kind of buffer for your messages, right? And if you have a big system with many queues, if those queues grow without bounds because your system, more stuff is going in than is coming out, then your system might become unstable, right? But if you have a concurrent programming framework that allows you to spawn threads, that will create queues any place that there's synchronization going on. So in particular, if you do in core async, you have 3 queues attached to every channel, right? There's the buffer of the values that are sitting in the queue, then there's the queue of the threads that are trying to send, and the queue of the threads that are trying to receive. And so you don't, even though you want backpressure and flow control in your program, you don't get it with the mechanisms that the API gives you. So, and I think the Clojure people should have spent more time on decomplecting their framework so that I could actually plug in the right mechanisms for backpressure here. So, getting back from the rambling. So you might have seen that, so little-known computer scientists of ages ago said this, right? In 2011, I sort of discovered the hard way. This is that really the language of Concurrent ML had shaped my thinking, right? And that it would, and if you have that at your disposal, everything else that comes after that is slightly disappointing. But also the fact that a lot of people have forgotten about Concurrent ML, specifically the people who've implemented Concurrent ML frameworks since then, really means, since they didn't have that language at their disposal, is their APIs turn out less powerful than they could be. So, if you want to treat this as a hierarchy, then there's Concurrent ML here. There's a new, well, it's not quite new, but a couple of years back, Aaron Turon wrote a great paper on reagents, and that's a mechanism that's faces a danger of extinction, but the OCaml people are picking that up, which is slightly more primitive than Concurrent ML, but it's based on very similar ideas, and that is also performant enough to not just implement concurrent systems, but also parallel algorithms. Core async, slightly less powerful. A lot of people refer to Horse CSP, which is nice, but Concurrent ML is nicer. And Erlang then gives you that specific combination of elements that give you all the advantages of OTP. But I really wonder whether you should see that as a straight line and whether there shouldn't be more branching points here that explore alternative designs. And I'm not currently seeing those, and I would like to see them in the future. So, as everywhere in programming, even though so some people don't believe that, but I believe you should really compose all the things, whatever you're doing, and Concurrent ML gives you that. And even if you don't get to do this in an industrial setting, writing concurrent programming, Concurrent ML, or any of the languages that implement Concurrent ML is tremendous fun. So I invite you to go out and do that, and it will put a smile on your face, especially if you've written concurrent programs that have not put a smile on your face in the past. But there's large open questions associated with this entire field, right? Is how do you combine composability with things like backpressure and distribution? And I don't know how to do that. I'm thinking about that, and hopefully at some point some results will come out, but it seems not as many people are working on that as there should be. That's all I have for you. Thanks.
Is it possible to model channels with a process in Erlang? I mean, couldn't you have that as the channel that you do the rendezvous on?
Yeah, but the fundamental problem is, so the question was, so that was my thinking in 2011, right? Because F# has the same model, right? Can't I just can I treat the process as a channel, right? But the problem is that you can only attach one receiving process to a channel, right? And the F sharp is the same way. So you can have a lot of writers, but you can only have one reader. And so that makes that picture asymmetric. And you know, I thought the same thing, but I invite you to try it, right? And that's going to be a not so pleasant experience. Yeah. So if you remember that F sharp code from that, it did exactly that, and I can assure you it works, but it's not pleasant. It kind of works.
No one else? Right. Thank you very much.
Okay. Thanks.